Hello, and thank you for joining our webinar today. Today we're going to be discussing in-building design using SignalPro. Now, as many of you know, EDX recently released SignalPro version 8.5.1. Among the new features in this release were some upgrades made to our in-building platform and the DAS design module. The version also marked the release of SignalIO, which is a new product launch that provides a full in-building design suite, as well as some of our outdoor to indoor, and indoor to outdoor planning features. Now, having said all of that, today we have an example of an in-building project, and we'll be walking through some of the features and best practices, particularly when addressing interference and reliability issues within public safety and simulcast systems. For that, I'm going to turn things over to Brian Jones, who will be demonstrating the in-building design software. If there is time at the end of the webinar, we will take questions. If you do have any questions, please use the question pane in the GoToWebinar dashboard. And do feel free to reach out to us after the webinar if you have any questions or want to see anything further with our in-building design software. So with that, I will go ahead and turn things over to Brian. Brian, go ahead and take it away.
Thanks, Bob. Hopefully you can all see my screen there, and hopefully you can all hear me. I wanted to start here with an outdoor project and talk about the sort of best practices that we have in SignalPro for planning simulcast type public safety systems specifically. EDX has been a major player in the public safety world for a long time, and we've included for a couple of years now with SignalPro a set of TSB88 recommended studies for planning simulcast systems and getting the reliability from those. And that's actually one of the distinguishing details between Signal and SignalPro, is whether you get those TSB88 studies. And that's true in SignalIO as well. If you have the SignalPro tool with our DAS design module, then you'll have those outdoor TSB88 simulcast studies. The SignalIO tool is still going to have outdoor studies and our indoor-outdoor studies as well, but you won't have those TSB88 studies. There's just sort of the more basic studies in Signal. And so let me talk through how I set up this outdoor project first, and also what the difference would be if I was planning this in Signal versus SignalPro. And then I'll transition into how I would take this project and add a building into it that I'm interested in and plan the indoor system, and then do some coordination between the indoor and the outdoor system. So to start with for this project, I've got just regular 30-meter terrain and clutter plugged into this. I wanted to keep this a simple project so that we had a nice clear example to look at. There are a number of methodologies out there that our customers are using for adjusting the propagation model and utilizing higher resolution terrain and clutter data. Our subscription EDX Cirrus clutter data is extremely detailed and granular, and there are a couple of different ways that you could leverage that data in your planning, but that's kind of outside the scope of this conversation today. So for this project here, I've plugged in just sort of base level 30-meter data, and the propagation model that I'm using for all of my path loss is just going to be the standard Anderson 2D with Fresnel zone loss. So you could think about it like I'm really just looking at the terrain picture here and not accounting for clutter losses and that sort of thing, just for the sake of this hypothetical. And that'll help sort of simplify the picture we're looking at. So my blue outline here is the service area that maybe I'm responsible for in my outdoor macro network. And I've imported a couple of sites here that are set to the correct frequency and have all the right height and transmit power and all of that. So the first step that I would do in Signal or SignalPro is just sort of look at the coverage layer. And I've already run these just to make things quick here. And let me get my legend showing while I'm at it. And there we go. Okay, so for this receive power at remote study, you can see the color scheme that I'm using here, and this project is in Virginia, near the Virginia Tech campus, and you can see the rolling hills. Even just with terrain alone, I've got plenty of coverage problems, plenty of little holes that I would need to fill in with repeaters or extra base stations, and if I were working with this project in Signal, I would go ahead and run my received power at remote area study, and I would also run a basic delay spread study. This one here, the simulcast RMS delay spread. So just to kind of review real quickly with simulcast systems, and that can be P25 or that can be Tetra if we're talking about Europe. The potential interference problem between sites that are all co-channel, they're all using the same frequency band and they're all transmitting at the same time, and the potential for interference is an intersymbol interference where the incoming power from a second or a third server is only considered to be interference if it is sufficiently time delayed from the strongest signal. And the requirements of the different P25 receivers or Tetra receivers can be a little bit different depending on your frequency band and the manufacturer and so on. And so the challenge is to predict those areas where the delay spread is going to exceed the allowable level for the C/I ratio that you have and guarantee coverage across the whole signal area, but also try and minimize that delay spread. So the simulcast RMS delay spread will look at all of the signals at each grid point, you know, all of the incoming signals from a base station, and it will take the strongest signal level and consider that to be the server, and then all of the other incoming signals will be considered potential interferers if they're within the mobile unit's capture ratio, and it will do a summing of the delay times for all of those signals within capture, where they're weighted based on their incoming signal strength. And the output delay time value is basically an adjusted delay time for all of those delayed signals coming in. So it's trying to account for all of the potential delays coming in kind of an averaged out way. The other one that we could do with Signal or Signal IO is the maximum simulcast delay spread. And that's where it looks at the signals, chooses the strongest one, and whatever the worst offender is in terms of its delayed time, it reports that worst delayed time. And so if I were running this project in Signal, I would want to run my receive power at remote and one of these delay spread studies and essentially try to make sure that I have coverage across the whole area and do not have any pockets where I have large delay spread values, or if I do have those pockets, I want to put them someplace where I'm not going to have users. And you can move around where the delay problems come in by adjusting the delay time on the base stations themselves. So let's say I want my site to the west here to be my main site that everything else keys off of. I would find the distance here and find the delay time, and maybe I'll delay this site to the east by 30 microseconds or whatever the distance is to try and sync it up somewhat with the other key site. And again, in this hypothetical example, I haven't put any simulcast delay offsets on my sites. I'm just letting the delay times out from the site be what they are and show delay in a nice intuitive way. So this could be considered like an untuned simulcast system that we're looking at here, or I haven't done any tuning of delay spread or adjustments that way. The SignalPro platform adds on the TSB88 studies, which these studies are under a special category, and they take a little bit of extra setting up so that we can handle the simulcast intersymbol interference problem in a more detailed way. The basic studies of, for example, the simulcast RMS delay spread, it looks at just the average predicted signal levels for all the base stations. And we know that in the real world, the signal levels from those different base stations are fading up and down all the time. So at any given moment, one site might be the strongest, and then in another moment, a different site is the strongest, and the delay time relationship between those two can be changing. You know, the timing is not going to change, but which base station the receiver is trying to hear may change, and so that, and also the power ratios of the servers may come closer to one another, which might impact how much delay time is allowable. So in the TSB88 study setup, the first thing we do is just specify the service area boundary. This is just a polygon. The blue line on my map here is my service area for all of that area that I'm interested in. And of course, I need to have my study grid set to be larger than this service area. And then we have this simulcast versus signal file, which this is just a text file, just like this, where what we're looking at here is a C to I ratio, if you will. So for example, if I have 30 dB of signal to noise ratio, and in this case, we're considering any other signal other than the strongest to be a potential interferer. If it's a co-channel signal, it's a potential interferer. And if I have 30 dB of C to I, then I can tolerate 8 microseconds of delay. But if I have 40 dB of C to I, then I can tolerate 12, and so on. And this performance curve will change depending on the technology that you're using, the bandwidth, so the actual channel bandwidth, whether it's 12.5 kilohertz or what have you, and based also on the manufacturer, these tolerances can change. So the best practice we recommend, if you really want to sort of do the maximum due diligence on a system, is to actually benchmark the performance of your receiver and find how much delay time is allowable at different signal to noise ratios. And once you have those numbers, what you would do is to go ahead and go under the utilities menu here, and there's a create edit simulcast curve file, and I would go in and add in the delay times and signal to noise values, and maybe a comment for each line if I want. And this will save out that text delay curve file so that you can go in under the study setup and point to it here. And then when we run the TSB88 specialized studies, instead of using sort of a hard and fast threshold for the allowable delay time or the allowable C over I ratio, we'll use that curve to determine whether each particular situation is a pass or a fail in terms of performance. I also put in the tile reliability that I'm looking for. And this has to do with the bounded area coverage study, where we ultimately want to say how much of the service area we have covered within an acceptable reliability percentage. So what percentage of the time the tile needs to be considered to be, viable, or have connectivity at that grid location. This is the percent reliability that's required for each of those grid points in order to be a pass. The required CPE or CPC is the required signal to noise ratio that you would like. And the standard deviation is the fading standard deviation. So how much the base station signal levels are going to be allowed to fade in each Monte Carlo trial that we do. And then, of course, a required simulcast delay offset. And again, these limits don't necessarily apply to all the TSB88 studies. If you want a really thorough explanation of what each one is doing, in the reference manual appendices, which you can get to from the help folder, there's a section here on the TSB88 studies that will explain exactly what each one is calculating. The one that I'm most interested in, and the one that's sort of the more general, does it work kind of a study, is the simulcast Monte Carlo reliability, where we're using that simulcast delay curve to determine a pass or fail for each grid point. And we do a Monte Carlo, a certain number of trials for each, 1,000 trials in this case, for each grid point to find how often it's going to pass with the delay and signal levels that it's seeing. And so when I once I've set up those prerequisites for the TSB88 studies, I can go into my area studies menu and set up the ones I want. And you'll notice here, again, they're under the study group called TSB88 Monte Carlo. And the simulcast delay spread study here still reports a delay time, but it's using the TSB88 method for calculating that delay time. And then the aggregate simulcast Monte Carlo reliability here, that's the one that's going to give me ultimately the percentage reliability at each tile location across my area grid. And so you can see here, I'm keeping a pretty strict requirement in order for the tile to be considered reliable, and anything lower than 95 or 80% reliability is going to be considered a fail, because obviously these systems are generally mission critical type systems. And so here's my my receive power, and I've got kind of marginal coverage in a lot of areas. If I show my simulcast delay spread, you can see there are little pockets where I get some larger delay times over on either side of the site. And when I run that Monte Carlo reliability study, here are the results I get. And you can see I've filtered that reliability study by my polygon, service area polygon here, just so that I'm not looking at results that I am not interested in. And you can see that there's kind of an area over close to each site where if the signal level becomes marginal from the dominant site, then the reliability can really be impacted by the long delay time from that second site. So for example, if I'm standing over here to the west and I'm getting a lower signal level from this ABAA, then maybe the signal level from the more distant ABAB is nearly equal, and that is going to have a dramatic impact on the reliability, because I've got some 36 microseconds of delay time from that ABAB site. And so again, maybe what I'd want to do is delay one of these sites versus the other, or do what I can to try and improve the coverage locally around ABAA and maybe down tilt these antennas to prevent them from sending energy so far away. But so this is sort of my starting point here for my outdoor system. And I'd like to transition now into what I would do if I have an indoor building and I need to add a simulcast DAS system or a P25 DAS system into that building. But then I also want to make sure that I'm not causing interference just outside the building or getting interference from the macro network. So I'm going to use the DAS module to model my building first. And I've got here, let me jump to another project folder. I've just made a copy of my project folder and added in some DWG floor plans that I've got, that each one of these is a flat AutoCAD floor plan of one floor of the building that I'm interested in. And what I'm going to go ahead and do, and let me jump to that other project. So I'm looking at the same general area here, and I've zoomed in and put a little star right where this building should go. This is the Virginia Tech campus, and this building right here is called Durham Hall. And I'm going to go ahead and open my building editor from the toolbar here. And I'll go ahead and maximize that. And then if I had just one floor, one DWG floor plan, I can just import that and away I go. But if I have multiple floors, I want to stack those on top of each other and make them into one cohesive 3D building. So I'm going to use this import floors from DWG. And I'm going to point to the folder that has my, my DWG files in it. So I'll go into EDX projects. And there's my folder. I also want to click on the setup here. And here I can give names and the index for the floor and so forth, but I give a base height and a height increment for the floor. This is the height above ground level that the floor starts. And in some cases, you may have overhangs or parking garages or that sort of thing where an outdoor signal can get in under it, and you want to be able to show that. So you might have a base height here that's other than 0. The height increment is the spacing between floors. And if you have a building where some of the floors are spaced differently from others, that's not a problem. You can go in after the fact and change these heights, but this is going to be the starting value. I also want to pick the floor material type that separates each of these floors. So I'm going to go with my solid reinforced concrete. And my import unit here, this is the units that the AutoCAD file was saved in, the unit of measure. So it'll typically either be centimeters or inches or maybe meters. And in this case, we're working with inches. So I go ahead and click OK. And I'm going to add each one of these in order. My floors are 1, 2, 3, 4 here. And you can see it's stacking them on top of each other. And I go ahead and hit this convert to MDL. And here it's telling me where it's going to put my building model file. And I also have some geoframe settings. Since I'm trying to put this building in a specific place on the earth and look at the outdoor to indoor situation, I need to make sure that I position this correctly. And so I happen to know that the origin point for my AutoCAD file, I've got some coordinates to go with it. 497. And so I can punch these in. Again, this is something that I can adjust after I start the project. So if you don't exactly know the origin point for your AutoCAD, you could start with just sort of the rough coordinates where the building should be, and then adjust it using our transform tools once you have the model. So I'm going to go ahead and click OK. And I'm using my standard material characteristics file for this example. And you'll see what it's done here is gone ahead and pulled in these AutoCAD drawings and given me 4 different tabs for the 4 different floors, which ideally should all line up with each other. Occasionally, you might find it where a client sends the files and they don't line up at all. And if that's the case, you would use this coordinate transform tab here, and I can move things a given distance in the X, Y, or I can just click on a couple of points and move things that way. So if you do need to do a little bit of work to line the floors up with each other, that's no trouble using this coordinate transform tab. And so what I want to do once I've got this pulled in is to make this into a decent path loss type model. You know, I don't necessarily want to include these door sweeps or the arrows up the staircases or even the stair facings themselves. Those aren't really useful from a path loss standpoint. And so I'd like to clean this model up basically. And the easiest way to do that very often is just to look at the different layers on the left here. And for example, this layer called 0 is all of my door sweeps. So I'll just go ahead and delete that out altogether. And I can go through, here's most of my actual solid walls. And then I've also got a layer that's windows, and this is all my glass. So it's really those 2 layers that I would want to keep, and most of this other stuff can go away. I've also got a layer called door here on the first floor with some metal roll top doors, and I can go through first and set different material types to all of those walls or elements that I want to keep. So for example, this door layer, I know those should be steel roll-up doors, and I'm going to go in here and do set wall material type on entities. And I'll select door, and then I'm going to change all of that to, oh, I guess I don't have metal in this list here. So maybe for the moment, I'll just set this to RF transparent. And there are no base and tops on these just straight walls, so I don't need to worry about that part. And then for the windows layer, maybe I'll do the same thing. And I'll change this to clear glass or UV blocking glass. There are a number of different products on the market that will behave differently at different RF frequencies. So it's likely that in your own projects, you will wind up expanding this material characteristics table to include other types of glass and maybe other wall materials, different metal products like those roll-up doors and things like that. They can all be added into this table, the wall material types as you need. So I'll do that with all the wall material stuff that I intend to keep. And maybe there are layers that I want to see in my map, but I don't really want to keep them as propagation elements. With those, I can go in and set them to be that RF transparent material type, and you'll still be able to see it in the model, but it won't have any impact on the actual path loss when you calculate your studies. So basically, I would go through and do this cleanup process on all 4 of my floors here, you know, get rid of my title blocks and this kind of stuff that you see outside the building. And when I'm happy that I have a nice clean building model, I'm just going to go ahead and save that. And you'll see if I go back into my project here, what it's made for me is an MDL file, and that's an indoor design building model file for EDX. And so now that I have that MDL file, I can import it into the project that I'm using, or I can start up a new project. And again, I sort of pre-cooked a lot of these so that you guys wouldn't have to wait while I put them together. So let me jump over to one that I've got done for indoor. So first I'll zoom way out here, and you can see I'm situated within that same area. I've got my same two macro outdoor sites, and then right in here on the Virginia Tech campus, I've put in a new study grid at a much finer study grid point spacing here, so that I can, oops, here, let me reopen this project so that I don't lose my studies. Yeah, there we go. Yeah, so if I had used the same study point spacing and study grid as my macro outdoor project, this entire building would have been contained in just a couple of grid bins. So I drew myself a study grid and went down to a much finer resolution. And I've also changed my propagation model here to deal with this indoor-outdoor situation. So under the category called specialized, if you have the DAS design module either on SignalPro or with our new Signal.io tool, you'll have access to this specialized category. And that's got the EDX simplified indoor model, which is a purely indoor propagation model that it uses a couple of path loss exponents to build some additional loss for just propagating through an indoor space. And then it also applies a loss every time the signal crosses through a wall or another material type. And so that indoor model is what I would use if I was doing a strictly indoor project and just laying out a DAS network inside of a building. But since I want to look at how the signal is getting out of this building and also how the macro outdoor signal is getting into this building, I want to use the Anderson outdoor to indoor model, which it will look at the entire path. And for the in the case of the macro outdoor sites, for example, it will use the Anderson 2D outdoor propagation model all the way up to the first building wall, when it at which point it transitions into our simplified indoor in-building model, and you'll start accruing extra loss for being indoors, and it will also start accruing loss every time it has a wall crossing. So this Anderson outdoor to indoor model is appropriate whether you're doing indoor to outdoor studies and you want to see how the energy is getting out of your building, or whether you're doing outdoor to indoor type studies and you need to look at the coverage inside the building, deep inside particular rooms from a macro outdoor site. And this model is adjustable both by adjusting the path loss exponent here and also adjusting those wall crossings. But then if I'm using clutter data for the outdoor component of my model, I can also adjust the heights or the path losses associated with that clutter. So this Anderson indoor to outdoor model is also very tunable if you have outdoor drive test data and or indoor walk test data from your network. You can use those to inform this model. And that would be a whole topic in and of itself. So just to make you aware, this model is very tunable. And so if you're not seeing good correlation between your walk test data and this prediction in your first study, it's easy to adjust those, and you can contact support to help you out with that. So once I have my propagation model set up and I've set a new study grid, you can see that I went into databases here and buildings and floor plans. I chose the MDL type for my building model type, and I pointed to the folder that has my MDL file in it. Now, if I have multiple MDL files, let's say I was responsible for all of the Virginia Tech campus, and they sent me a collection of these AutoCAD drawings for every building, I could put all those MDL files together into one folder. And when I set up that database, then this pull down will be able to, I'll be able to select from different buildings and go in to look at the DAS systems in each one of those buildings. If I leave it set to all buildings, it really only looks at or it looks at all the buildings together and is kind of looking at the outdoor case instead of looking at any specific floor. And as soon as I choose a building, I also choose a floor height to go with it. And so if we're talking about an outdoor study and I choose a floor other than one, the indoor results will be on that floor and the outdoor results will be on the ground at whatever height the mobile unit is above ground level. So the first study that I set up here, I should talk about my groups first. Since I have those macro outdoor sites, I went ahead and created a group called macro sites and put just those in it. And then I'll also have a bunch of sites in my master DAS group once I get done designing my DAS system. So let me talk about that real quick for the moment. What I did first was I went ahead and ran a receive power at remote for just my outdoor sites. And you can see the signal levels that I'm getting here are reasonable. This would potentially be a good connection for a mobile that's out here, but they're not extremely strong. So it's possible that some energy from one of my indoor antennas might get out and interfere with a mobile in this outdoor area. So for example, somebody standing in the parking lot here might have a good signal from the outdoor site, but because the delay time on this in-building site may or may not be aligned with the outdoor, there's a potential that I might have some interference there. And so for designing the DAS network, I can go in here and let me get in close to my building and turn off my Bing map layer so you can see this. I've got, under the DAS menu here, I've got my building equipment list. And I can choose from different RF sources, cables, and antennas, and basically connect those together. So just for example, if I, that's why. If I wanted to add an antenna or a couple of antennas on a splitter, I don't know what happened there. One moment, bear with me, please. Okay. So let's say, for example, that I've got a transmitter or a BDA, something to that effect, in a closet here, and I'm going to put my antenna out here in the hallway by the elevators. I can stick my antenna here, my RF source, and then I choose my RF cable tool here, and I'm going to connect it from the RF source to the antenna. And, you know, I can put splitters to add additional antennas and all of that sort of thing. And this is how I would go through and design out my DAS network for in building. And you can see we've got tools here for standard cable and also for DAS or optical cable. And we've got DAS hubs and remotes. So I can distribute a signal optically around the building and then use a DAS remote to transition that back into RF energy and attach it to an antenna. Rather than do a bunch of complex cabling and antennas on every floor and things for this example, what I did was just to use my AP object, where it's just a self-contained transmitter all-in-one. And I went ahead and set up an AP that's on the same frequency as my outdoor public safety systems. And I put this in a hallway. There's a bunch of little offices here that have nice big glass windows that this is standard clear glass. And we've put a repeater or a little access point out here in the hallway for my simulcast system. And when I go ahead and run the receive power for that site and back out here, or that antenna, you can see I am sending quite a lot of energy out into the parking lot outside the building through those glass windows. And so this is potentially going to cause that interference that we talked about. And I can take my my antenna and maybe move that deeper into the building in order for it to, keep its energy more contained within the building. And the best practice for sort of showing the separation between the two studies, or the best study to use, is called the C/I ratio, primary group TXs to second group TXs. And so again, I've got my two transmitter groups here for my outdoor sites and my indoor sites. And if I go into my area studies list here, you can see I've set up a receive power at remote study for just the DAS system. So in this case, there's only one thing in that DAS group, and that's the access point that I added in. And for any of the studies that are using the Anderson outdoor to indoor model or the simplified indoor model, the calculation method here is going to need to be direct to grid. If you set this up and try to set it up with a radial line study, it'll throw a warning message and tell you this needs to be direct to grid, because that's the only way to make sure that our wall crossings are done in a very precise way. We need to know whether or not we're crossing through any wall elements, and that can only be done on sort of a point-to-point, direct to the grid point center basis. So I set that here. I put in a display threshold and set up the mobile remote unit that I'm using for the study. And so I've got one of those for my DAS, one of those for my outdoor sites. And then in order to show the relationship between the two of them, I'm going to choose the C/I ratio primary group to second group. And you can see I've got macro sites as the primary and the DAS group as the secondary. So this study is always going to treat the outdoor sites as the desired signal and the DAS as a potential interferer. And when I go ahead and run this study, oh shoot, I wish I hadn't done that. Well, I meant to just show that study instead of running it, but now that I've started, I have to wait for it to complete. What this is going to show is that I've got a lower or a negative signal to noise ratio in this parking lot, where the signal level from the DAS is stronger than the macro system. And the question has come up a lot recently from various users, how can we coordinate the timing of that indoor DAS system with the macro outdoor network? And the more I've talked with a few of our different users who are kind of into the details of the hardware, the more we're finding that's a really complex and possibly kind of intractable problem, because every active component in the DAS network has its own latency time. So any repeater or an optical hub or remote, the BDA cabinets themselves, those all have their own latencies, and the actual latency time is not necessarily consistent from device to device. So even if I have the exact same BDA cabinet, the exact same model number from the same manufacturer, there might be differences in the effective latency time for each one of them. And it's also somewhat dynamic depending on different factors for the equipment, its ambient temperature and what the bandwidth that it's operating at is. And so what we're finding is that it's kind of impractical to really benchmark and test every single device in a DAS network for an in-building system, but the delay times within the DAS network, within an in-building system, are almost never going to exceed the allowable levels. So you don't really need to worry about simulcast delay spread within the building itself. You just need to worry essentially about isolating that system from the outdoor system. And in our contacts with folks at the TSB88 committee and again, users who are kind of very focused on the equipment, what the sort of best practice that we've been finding they establish is to use the C/I ratio as the main indicator of whether or not the two systems, the outdoor and the indoor, will sort of get along with each other. And the best way, or the sort of the benchmark that we've been hearing, is 12 to 15 dB of isolation between the two is sufficient to ensure that even if there is a large delay spread between the two systems, it's not actually going to degrade the audio quality or result in significant intersymbol interference. So in short, the way I would fix this potential problem, and so I've got my results here. If I only show the study layer and set it for the status bar, you'll see in the status bar here, out here in the green area, my outdoor network has 25 dB or more of signal noise ratio, and therefore it's going to be just fine even if there's some delay spread between the indoor and outdoor system. However, as I get around to this side of the building where partially I set this up on purpose, my outdoor transmitters are to the south, and so I'm standing in the shadow of this building from the standpoint of those outdoor sites, but then I've got this indoor site right next to a glass window, and it's possible here that the mobile unit is going to hand over to talking with the indoor DAS, but it's really in these boundary areas where the power levels start to approach each other. You know, I'm down to 5 dB or so on either side, and that's where I'm really going to get a high probability of intersymbol interference. And so the solution to that, again, would be to maybe come in here and try to pull this deeper into the building and see if that corrects the issue enough. Or maybe I would reduce the power coming from that access point, or, you know, there's a lot of different remedies that I could use, but ultimately I would want to go and run this C/I ratio and find that I'm getting a good ratio both inside the building and outside. And I could run this primary to secondary study going the other direction as well, where I set up the DAS network to be my primary group, and I set up the outdoor network to be the secondary. And there I'd be looking for, you know, all decent C to I values within the building, and not to see any red. The danger might be that I would see low C to I ratios when I'm close to the windows, which would indicate a potential problem where the outdoor network is interfering with the indoor network once you're inside the building. And these are really the kinds of problems that are being reported by folks who are deploying these types of networks. Is, you know, the signal levels and performance will all be good on the macro outdoor side out on the street, and the signal levels will be good inside, you know, deep inside the building itself. But it's those boundaries where you're right outside the building or right inside the building where the one system will interfere with the other. And so we're really just trying to maximize that C to I ratio for both. And we'll let this finish up real quick here. And then I'll take a look at making sure that we have coverage across the service area, either within the building or for the outdoor network. And then I'll kind of wrap up here. Okay, so you can see that moving this site out of the hallway did cut a whole lot of that energy that was going out into the parking lot. I've still got a little bit of potential problem here, and I could pick a more granular study point spacing if I wanted to see just how bad this really is. It looks like some of my signal is coming still out through these glass windows. But that would basically be the process for trying to isolate the indoor network from the outdoor network. And at this time, I'd love to field some questions if there are any. Your go-to webinar panel has a questions item there that you can expand. Feel free to type the question in and then click send privately or send to all if you'd like me to try and address something particular. While you're doing that, I wanted to jump over to a different DAS project here and show you kind of a more complete project, a more complete indoor project. So let me jump over here. And this would be that indoor Durham Hall project with some more assets in it. So what I've done here is up on floor 4, I have a BDA cabinet, an RF source here. That RF source, I've put it right next to a riser. And what the riser object here does, this is a tool on the toolbar, is that'll connect the floors to each other. And so what I've done is from that RF source, I'm going into a little optical DAS hub and sending optical cables over to a DAS remote and an antenna here, and then sending some more into this riser and down to other floors so that I can run my coverage studies for each floor. And you can see I've got a little bit different footprint on each floor, and I've got my options set up here so that the study is using all of the transmitters, so I get some signal fill from the antennas a floor above and a floor below. And in that way, I've kind of designed the offsets between my sites to cover this building. And again, if this were public safety, I'd be wanting to find some way to control some of this energy getting out of the building if possible. Let's see. Couple questions here. There's a question, are there any 3D export options for the coverage footprints? And essentially, the coverage prediction itself is still a flat 2D picture. So let me adjust my map view here, and hopefully you can see this is sort of on a plane. Where this this study is going to be displayed at its height within the building, but it's still a flat plane. So the building is being treated in 3D by the propagation model, but the coverage footprint, or the study itself, is still a planar look, and each floor is its own plane, if that makes sense. Let me get back to my project here. Hang on one moment. I'm trying to read these. There was a question about the bill of materials. If I go again into my DAS menu here, once I have this whole thing laid out, I can get my bill of materials for the whole network, or if I click this show each cable run, it'll show me each of the lengths of cable that I've used. And if I have any incomplete circuits, so if I have antennas that don't have anything connected, or cable that's going off to nowhere or anything like that, it'll show me errors here, and I can have it list any of those errors and point out where I've got things that are incomplete. The other thing that we can do is go into the building editor here, the DAS design editor, and I have all the ability to move stuff around and edit the building is available in this tool, and that includes the various RF components. Some of our users have reported that since they built the building in this tool, they really like working with the DAS components themselves in the same platform. And so you can do that here, and you can even run quick studies, although they're just power studies. It's not comprehensive like they are within SignalPro. And the schematic view here will show, how I have everything connected together on each floor. And so these can also be printed and exported in addition to the bill of materials. We had the question, can this be used for tunnels? Yes, it can. There are some caveats, and sort of, it takes a little bit of special setup to make sure that you're doing a good job with representing the tunnel within the building editor. But the main thing that often needs to be used in tunnels for mining or subway tunnels or any of that kind of thing is the leaky coax or radiax type distributive antennas. And you can use those in here as well, where I would connect from my RF source and connect from leaky cable out to some terminator, like an RF attenuator out on the end. And that will treat the entire length of that cable as the antenna location, so that you can run those leaky cables all the way down a long tunnel and make sure that you've got coverage sort of across the platforms and et cetera. And again, if you want to discuss tunnel design in more depth, that's definitely a good conversation to have offline. There's a question about the signal quality DAQ 3.4 or getting to your DAQ levels. And that's really a question of how the manufacturer of the equipment, whatever the receiver is that you're using, it's going to have specifications for what it requires to achieve that DAQ 3.4. And that'll either be a signal to noise ratio, or sometimes it's just a raw received power level and a spec for the allowable delay spread. And so depending on the equipment or on the information that you have from the equipment vendor. Usually the way you would set up a study to show a particular DAQ level is, actually, let me jump back to my other project real quick. I'll jump to the simulcast one. And so I've got my C/I ratio study here. I would set that up for the indoor case so that we're looking at the DAS group as the primary, and each of my different signal and color levels here, I would associate with a different DAQ. So if, just for the sake of argument, if the particular receiver I'm using says that it needs 9 dB of signal to noise ratio to hit DAQ 3.4, I could put a label in here, DAQ 3.4, and it'll associate it that way. For my macro outdoor simulcast, I will use the reliability study associated that way instead. Because, you know, the reliability is giving you the percent of time that you're meeting all of the receiver's criteria, both in terms of signal to noise and in terms of delay spread time. So, you know, showing what percentage of time you have that DAQ level, you know, whatever the acceptance criteria is for your DAQ level, you can use that reliability, simulcast reliability study to show that. There was a list about, or there was a question here also, one last item, and then I'll close up. And if there are any other questions, please email us after we close down here. And there was a question about the wall material types, and the wall material file that comes with the software, this matcare.dat, has some default material types and losses in here that are mostly from the Rappaport text on RF wireless or wireless network design. There are a great many of studies and experiments out there where folks have showed the amount of attenuation you get at different frequency bands for propagation through various wall material types. These initial ones that EDX provides are a good starting point that are sort of the best bet default values for across various frequency bands. And this is really kind of the most comprehensive table we have at the moment. We don't have a big database of wall material types and their losses, mostly just because those types of experiments tend to be either extremely focused on a particular frequency band and a particular wall material product, or they're proprietary and you know, people aren't publishing that data. So that is something where if you have a particular engineered surface or a particular you know, strange wall material type of some kind, you might want to set up some way to measure the propagation across that and input that as a new wall material type, or, you know, reference from various sources what you should expect in terms of loss for, you know, the steel containers or whatever your particular case may be. So that's kind of the ground that I wanted to cover here today. Again, if this brings up more questions or you'd like to get into more detail, feel free to email either myself or Bob at sales@edx.com, or get in touch with support@edx.com if you need some help getting a project like this set up on your end. I appreciate everyone taking the time today, and if there's anything we didn't get to, I hope you'll send us an email. Bob, did you have anything additional to add?
Nope, sounds good to me. Thanks, Brian, and thank you everybody for joining. And yeah, definitely let us know if there's any questions or any other follow-up items we can address for you.
Okay, great. Thanks, everybody.